Okay, so I think we can start. Welcome everyone to the 1W-MINDS seminar. I'm extremely happy to introduce Tselil Schramm today. Tselil is a third computer scientist. Her affiliation is somewhat in transit. She was just recently at MIT and Harvard. She's visiting Microsoft, and she's going to join as faculty in Stanford Statistics in a few months. Tselil's work is mostly in understanding average case complexity of problems that arise in high-dimensional statistics and data science, things of this type. To highlight one that I particularly like, I really like her paper where she and collaborators prove that the power of sum of squares is essentially matched by spectral algorithms for a large class of problems arising in high-dimensional statistics and related things, showing that if one proves that these sort of very expensive sum of squares hierarchy can do something, you can actually do it much cheaper. And to me, this is excellent result. And actually today she's talking about something a bit in the same vein, where she shows that two ways of thinking about average case hardness will actually match in a lot of interesting problems. And I'm super excited to hear about it. Still, take it away.
Thanks for the very nice introduction, and also for the invitation. Super thrilled to be here. So yeah, I'll be talking today about, just like Afonso said, reconciling two different frameworks of average case hardness, hardness for statistical queries, and the low degree likelihood ratio, which is hardness for low degree polynomials. So I'll explain everything as we go along, but this is joint work with my excellent co-authors, Matt Brennan, Guy Bressler, Sam Hopkins, and Jerry Lee. Yeah, so let's just get right to it. I should say that the paper is not yet on arXiv, but in a week, hopefully it will be. So that's just to put some pressure on the team that's writing the paper. All right, so let's get started. So the context for this work is studying information computation gaps. So in high-dimensional statistics, in general, what we have is we have a bunch of data points. So we have our set of data. Usually we think of the number of samples, which we denote by n, and also the dimension, which we denote by n, as going to infinity. And the high-level picture is that we take this data, we feed it to an algorithm, and we want to get some conclusions about that data, whether it be inference or estimation. And because we are greedy, we want our data to be noisy. So we want our algorithms to tolerate very noisy data, but we want our algorithms to still be fast because we don't have a lot of time. But in many cases, what we observe is an information computation gap. That is that noisier data requires slow algorithms. So once you have data that's sufficiently noisy, fast algorithms no longer work, and we have to resort to things like brute force search or slower algorithms. And this phenomenon is ubiquitous both in practice and in theory. So meaning that it already shows up in many model problems. So I'm just going to throw out a couple of problems right now, and then I'll explain one of them a little bit in detail. So for example, for planar clique, tensor principal components analysis, sparse principal components analysis, community detection problems, and many more. Okay, so let's take as a case study sparse principal components analysis. Oh, yeah, there we go. Sparse principal components analysis. So in this problem, we see m samples. Each of them is a vector in Rn. And these samples are sampled from a Gaussian distribution where the covariance matrix is given by the identity plus a rank 1 spike. And this spike is a unit vector. And it's also a sparse unit vector. So it has k non-zero entries. And typically we think of k as being something like less than n over 100, but more than root n. Okay, so this is the sort of interesting regime for the problem in any settings. And you can think of it as follows. You can think that, for example, maybe each sample that we see is the results of a patient genetic test with many genetic markers. But this pointed vector v marks the genes which explain the symptoms. Okay, so what we want to do is we want to take in all of these samples and we want to recover this special direction v. All right, so how many samples do we require? It's not so difficult to show that once the number of samples is at least something like k log n, you can recover via information theoretically, meaning the maximum likelihood estimator will be v. But for polynomial time algorithms, we actually need, we actually observe that we need at least quadratic in k many samples, okay? So this here is an information computation gap. Because in order to have efficient algorithms succeed, we need many more samples by a factor of k than in order to succeed information theoretically. Okay, so the question is, how should we explain the hardness of computation for this problem when we don't have enough samples? So in classical complexity theory, the strategy is like this. You take all of your problems, for example, 3-sat, maximum clique, etc. And what you do is you want to arrange them according to their computational difficulty. And the strategy for doing this is via reduction. So you say, if I can solve the 3-sat problem, then I can also solve the max clique problem and vice versa. So each of these arrows is a reduction between two problems. And then the problems arrange really nicely into equivalence classes according to their hardness. So for example, there's a class of NP-complete problems. There are a bunch of problems which we're not sure if they're NP-complete. There are problems that we can solve in polynomial time. So classical complexity would prescribe that we take a similar approach in the statistical setting. But in the statistical setting, things aren't so easy. So while we do know some reductions between problems, for example, there are reductions between sparse PCA and planted clique, or to some extent reductions between tensor PCA and random 3-sat, the problems are qualitatively different enough that it would be very difficult to imagine a reduction going from random 3-sat to mixtures of Gaussians. The issue is that you don't only care about the formulation of the problem itself, but you also care a lot about the distribution. And so it's very difficult to get reductions that respect these distributional properties. So the strategy of classical complexity seems like it is not going to be a fully satisfying theory here, even though there have been many advances along these lines in recent times, but I won't talk about that today so much, because what's more relevant to us is the more kind of popular approach, which is to say, okay, we only know a couple of polynomial time algorithms really. I mean, they organize into general classes. You know, we have our convex programs, we have our spectral methods, we have, you know, algorithms that are based on statistical queries, we have Markov chains. So what we're going to do is we're going to rule out specific models of computation. So for example, you want to study the sparse PCA problem, what researchers do is they rule out these algorithms one at a time. So you say, okay, can convex programs solve sparse PCA with fewer than k-squared samples? The answer appears to be no. So you still need m greater than k-squared. Can spectral methods solve sparse PCA with fewer than k-squared samples? Here it's not quite, you know, it's hard to make this comparison, but the answer is still no. You really need at least k-squared samples, etc. You know, researchers go around and rule out one of these classes of problem algorithms at a time. Okay, and I should say that, you know, each of these papers is fairly sophisticated and requires you know, quite a bit of effort. And if our strategy for dealing with average case hardness or statistical hardness is like this, very soon we're going to end up with a complete bipartite graph like this. Okay, so it's not the case that for each of these problems we know each of these kinds of lower bounds, but if this is our plan, let's realize that each one of these lines is a paper. It's a whole paper, right? And every time you see a new problem, you have to do it all again. So this proliferation of lower bounds is fairly undesirable. And maybe there's a different way that we could hope to do this. Okay, so maybe instead of having reductions between problems like we do in classical complexity, we can have reductions between algorithms. That is, we say, anytime that convex programs succeed, then maybe some other algorithm like spectral methods also succeed. Or we say, you know, low degree polynomials are no more powerful than convex programs. And then what we could do is we could take sparse PCA, we could only prove one lower bound, And then based on that lower bound, we can get lower bounds for each of these different approaches. So this is kind of like the, the Iceland Air strategy for airplanes, right? So instead of having n squared planes and for each of the pairs of cities on the different sides of the Atlantic, they have, only order n planes with Iceland in the middle as a hub. This joke is taken from my co-author, Sam Hopkins. So maybe we could do the same thing, but for average case complexity, and endeavor to have instead of having n squared papers, only have order n papers. Okay, so this sort of line of work already exists. I mean, this research agenda has been around for some time, and there are a couple of highlights that I want to bring up. So one such highlight is a reduction from some classes of convex programs to statistical queries. So this is due to Feldman, Guzman, and Vimpala. But there's an asterisk here because you really only rule out some restricted classes of convex program. Restricted class. So if you're willing to tie the hands of the convex program behind its back to some extent, then the convex programs are no more powerful than a class of algorithms called statistical queries. There's a sort of a folklore reduction from spectral methods to convex programs. So anything that a spectral method can do, some kind of convex program can do as well. But in the reverse direction, a paper of Hopkins et al. Hopkins, Kothari, Patachin, Raghavendra, Schramm, and Stoyer from 2017, it shows that if you are willing to restrict your attention to noise-robust problems, then convex programs are captured by spectral methods, although the quantitative loss here is a little bit undesirable. So there's like a asterisk that's like quantitative. Okay, but at least the idea is that convex programs are captured by spectral methods. And then a very recent exciting work of Gamarnik, Jagannath, and Wine show that at least low-degree polynomials and Markov chains are both related to a different property called the overlap gap barrier. This is basically some feature of the solution geometry. And they show that when the overlap gap barrier exists, both of these types of algorithms fail. Okay, so this isn't exactly a reduction between algorithms, but it's saying that there are common problem features that can cause both of these algorithms not to succeed. And then if you can show that some problem, such as Sparse PCA, has an overlap gap barrier, then neither of these algorithms will work. Again, like here, maybe you could hope to strengthen the quantitative results a little bit. But yeah, that is the context for our work. And today what I'm going to show you is I'm going to show you the following results. So low-degree polynomials and statistical queries are equivalent. SQ is equal to low degree. This is for the problem of hypothesis testing. And the result is, it holds true under fairly general conditions to the extent that we can capture at least all of these problems in a quantitatively very tight sort of way. So I'll explain more about that on the slide. Also, if people have questions, I guess they should be asking. Yeah, at any.
Yeah, there is a Q&A box that people will ask questions on, and then I'll read them and ask. Yeah.
Excellent. Okay, I just want to make sure that that people are following. Okay, great. So, all right. So let me spend some time setting the statement of the main theorem up. This is just the overview, but I'll explain what I mean by hypothesis testing, and then I'll introduce the low-degree polynomial framework and also the statistical query framework. Okay, so our setting is going to be many versus one hypothesis testing. So this whole time I'm going to use Sparse PCA as an example to illustrate what's going on. So in this setting, we have some null distribution over Rn. So for Sparse PCA, you can think of the null distribution as just being a Gaussian with zero mean and identity covariance with no spike. And we also have a set of alternate distributions. A. So here maybe think of the alternate distributions as being the distributions that are normal with a spike. So I have a set of distributions U indexed by these vectors U, which are sparse vectors. Okay, and then I also typically think of having some distribution over the elements of A. So maybe here I think of my distribution as just being uniformly random over A. And you can just think of it that way for the rest of the talk, even though in the hypothesis testing problem, there's flexibility to choose this distribution. But so now A will be uniform over Gaussian probability distributions with sparse rank 1 spikes. And our task is as follows. We're given n samples from one of these probability distributions. So either m samples from the null distribution or m samples from one of the alternate distributions inside the alternate hypothesis class. And our goal is to design some algorithm theta, which looks at all of the samples and either outputs alternate or null. And what we want to do is we want to minimize the probability that the algorithm gives the wrong answer under the null distribution, plus the probability that the algorithm gives the wrong answer when given samples from the alternate distributions. Okay, so that's the...
Still, I have a quick question, sorry. What, does the algorithm know the distribution of the mu's?
So the algorithm knows A, right? So yeah, so the great point. So the algorithm knows A, it knows what the alternate hypothesis class is. It knows mu, let's say, but it doesn't know which of the DUs it's getting samples from. Right, so.
But then why is this many distributions and not just one distribution that's a convolution of mu and I guess D?
So suppose that you knew what the distribution U was in advance, right? Then it would be really easy to test for that specific distribution U sometimes. Okay. But the fact that you have a larger class of distributions makes it harder to test. So this sort of captures the paradigm that I was explaining before. Like, let's look at the example of sparse PCA. You know that there is some sparse, you know that in the alternate case, there is some sparse direction in the covariance matrix, but you don't know what the sparse direction is. If you did, you might not need so many samples in order to figure it out. Yeah, great question.
I see, okay.
Okay, so the nice thing about this problem is that it's sort of a simple, it's like a simplified setup. So if you're used to thinking like a complexity theorist, you can think that, you know, in complexity theory, we have search problems and we have decision problems, and decision problems are sort of easier to study. So hypothesis testing is like the decision version of estimation. But many of the phenomena that we see in high-dimensional statistics already show up for the hypothesis testing question, for example, information computation gaps. Okay, so for sparse PCA, for example, we see the same type of gap where we only need k log n samples to information theoretically distinguish, but we need k squared samples to distinguish or to hypothesis test efficiently. Okay. All right, so one class of hypothesis tests that you can design are the following class, called a low degree polynomial hypothesis test. So the setting is like this. What I want is I want to find P.
Question. So when you say the number of samples you need to solve efficiently, is this polynomial time? The number of samples?
Yeah, polynomial time.
So you could still do it in, say, exponential time with the information theoretic. Okay. Thanks.
Right, yeah, the algorithm that you could do in the information theoretic limit, I mean, the best one that we know is to just check all sparse vectors and see if one of them aligns with the direction. Yeah.
Okay, that makes sense. Thanks a lot.
Right, yeah, I mean, it's actually like a more complicated picture where you can sort of smoothly interpolate from the kind of computational efficient algorithm threshold to the information theoretic threshold, and like Afonso, for example, has a paper on exactly this for sparse PCA. But yeah, this is the resolution that I want to study it at today. Efficient means polynomial time algorithms. Okay, so to our first restricted class of algorithms, low-degree polynomials. So suppose that I want to look at the following restricted class of hypothesis tests. I'm allowed to take a polynomial which takes in m samples from Rn. Okay, so it's a polynomial in the entries of my sample matrix. And my restriction on the polynomial is that it has degree at most capital V. And what I want to do is I want to maximize the expectation of this polynomial under the alternate hypothesis class, subject to having expectation 0 in the null case, having bounded variance in the null case, and having also bounded variance in the alternate case. So this would basically mean that, you know, I don't want this value t squared to be too much bigger than the value of the expectation squared. Okay, so the way that I'm setting this up, if this optimization problem has a large value, then computing this polynomial in the examples will give me a good hypothesis test just by applying Chebyshev's inequality, because I have large expectation in one case, low expectation in the other case, and bounded variance in both cases. Okay, so just, I mean, at first when you see this paradigm, it seems a little bit strange, but let me show how one very typically used class of algorithms falls into this framework, and that is spectral methods. So imagine again that we're in the setting of the sparse PCA problem. So I have samples, but now my samples come from the following distribution. Instead of having just a rank 1 spike, I have a rank 1 spike that is scaled up. So, right, so the only difference between the previous setup and this setup is that here I've multiplied this rank 1 spike by 100. Okay, so consider the following algorithm, which is kind of the classical principal components analysis algorithm. What I'm going to do is I'm going to assemble the empirical covariance matrix, right? This will converge to identity plus 100 PV transpose as n goes to infinity. And then what I can do is I can compute the top eigenvalue of this covariance matrix just by looking at sigma to the log nth power applied to some arbitrary starting vector. Let's say it's the you know, just entry in the top index, and looking at this norm. So if I'm in this planted case, the value here will be large, right? So this will be like the top eigenvector to some large constant. And if I'm in the null case, this value will be something like 1, because you know, in the null case, when this vector is gone, the eigenvalues are just all 1. It's just identity. Okay, so the value of this test gives me a hypothesis test for alt versus null, and furthermore, I claim that this is a degree order log n polynomial. So this is a degree order log n polynomial in the samples. All right, so this spectral method, which is, you know, one of kind of like the workhorses of statistical analysis, is in fact captured by degree log n polynomial tests. Okay, so now what I want to do is suppose that I want to study these low degree polynomial hypothesis tests. Well, as written here, this program does not have a closed form solution. But if I make one tiny change, the program will have a closed form solution. So if I just get rid of this constraint, so this is the relaxation. So now all I'm doing is I'm maximizing the expectation under the alternate distribution subject to expectation 0 under null and bounded variance under null. So I'm going to introduce the closed form solution to this program. So in order to do that, let me define the following inner product. So I define the inner product between f and g to be the expectation under samples drawn from the null distribution of fx gx. Okay, and now I can define the following function. This is the relative density of u. So this is like the probability under, So given a sample x, what this outputs is it outputs the probability that I see x under du divided by the probability that I see x under the null distribution. And just assume that the support of the null distribution always includes the support of the alternate distribution, so that this is always a non. I'm not dividing by 0. Okay, so the way that this is set up, if I take du dot any function f, this is like the expectation under samples from du of f. Right, and now it will turn out that the closed form solution to the program on the left-hand side is the following. So the opt of this is equal to the norm of du tensor m expectation over u projected to the space of degree capital D functions minus 1. Okay, here this is the norm with respect to this inner product. All right, so that was a lot of math on a slide, and I know it's impolite, and I apologize. But yeah, basically the point is that, you know, if I am willing to relax this program just a little bit, I can know what the optimum value of this program is. And so
there's can I ask a quick question? There's a question in the chat. So Prayag Vinkan asked if it could be an issue that the way this is defined as the vast low degree polynomial test, that it could be potentially very different for different values of m. And so be sort of an algorithm that depends very much on the size of the problem, and if there's any potential issue with being non-uniform in this way.
Oh, yeah, I'm sure that you can cook up examples where it really matters, but for many of the problems that we study, it's sort of not an issue. You have a sort of closed form solution that depends. I mean, as n goes to infinity, this value is nice. But if you want, you can think about it as solving this problem differently for every n and m separately, if you want.
I have also a very quick question. Why is the condition that you relaxed out? Why is it desirable? Maybe I missed something, because I usually don't think about it this way. Why would that condition be important?
Why would this condition be important? So if you don't have this condition, so suppose that you solve this program and you have this program without this condition. So you don't have a bounded error like in both sides. You only have bounded type 1 error. Right, the variance under the alternate distribution might still be quite large, and for that reason, you only get bounded error against rejecting the null distribution. And there's like a very easy test that does that. It always says alternate, right, or it always says null. So that's the issue. Like if you wanted to actually solve for the best polynomial, you want this constraint, but that's not what we're going to do. What we're interested in is we're interested in lower bounds. So taking this relaxation has no big deal. So basically, what we're going to argue is that, and that's exactly what it says on the next slide, if the, oh, sorry, I was going to give this a name. So I'm going to call this the LDLR M. So this is a degree D norm of the low degree likelihood ratio for M samples. So in the case when the D low degree likelihood ratio is small, we're still able to prove that no low degree polynomial can give a high probability hypothesis test, right? So if the not relaxed program had a good solution, we would get a good hypothesis test. But if we relax the program and we still show there's no good solution, then there's definitely no polynomial hypothesis test. All right, so so that's all fine and well. We have a framework. We can prove lower bounds against these low degree polynomial hypothesis tests, but why should we care? Well, the main reason to care is that surprisingly, this LDLR framework gives really, really good predictions. Okay, so for almost any statistical problem that you care to throw out, if you can show that degree, super logarithmic degree, low degree likelihood ratio is small, then all the polynomial time algorithms that we know fail. Why do I require this to be super logarithmic degree? Just because spectral algorithms are captured by logarithmic degree. Yeah, just because spectral algorithms are captured by logarithmic degree polynomials, as we said on the previous page. So, you can implement degree D, low degree likelihood ratio, like a polynomial hypothesis test in time n m to the d, just because this is the number of entries we have in our sample, and to evaluate a degree D polynomial, we only need nm to the d time. But if you're willing to make the degree D here like super logarithmic and show that there are no such polynomials, then we don't know any polynomial time algorithms. And this is true for the setting of planted clique and for community detection, tensor principal components analysis, sparse principal components analysis, many problems fall into this framework, and there are kind of conjectured conditions that can be met under which we expect the LDLR to give the correct prediction. Okay, so these are roughly some kind of noise, robustness, and symmetry conditions. And another reason why low degree likelihood ratio bounds are interesting is because they rule out other algorithms, right? So they rule out some spectral methods, at least those that can be computed with low degree polynomial matrices that have a sufficiently large spectral gap. Approximate message passing algorithms are ruled out. Some convex programs are ruled out. In fact, I mean, so this isn't a kind of a broadly true, but in several cases, starting with a low degree likelihood ratio bound, you can prove that convex programs fail, and that is kind of where this low degree likelihood ratio method originated, right, with the work of Barak et al. For planted clique. And then later extended by Hopkins and Stoyer and Afonso and co-authors and many others. Okay, so that's it for, I'll say one more thing. So in our work, we're considering a somewhat unorthodox version of the low degree likelihood ratio. So instead of using straightforward degree, we're going to use something called the sample-wise decay degree. So our polynomial is going to be supported on monomials that include at most k samples at a time and degree at most d per sample. Right, so instead of projecting to the span of polynomials of degree d, we project to the span of polynomials which have sample-wise degree dk. All right, so we call this the dk LDLR. And the reason for this is because it very much simplifies a lot of our proofs. It's possible that we could consider the standard notion of low degree likelihood, and then one point that I want to make is that the dk LDLR is upper bounded by the d times k LDLR. So these two quantities aren't actually so different. Okay, so now on to our second model of computation, which is statistical queries. So in the statistical query setup, what you have is you only have oracle access to your distribution, right? So you're interacting with a distribution. What you get to do is you get to ask queries to a vstat t oracle. So for any function whose output is bounded between 0 and 1, vstat t will give you the expectation of that function over your distribution up to a tolerance of plus or minus 1 over square root t. Here there's some asterisk for functions that are very biased, but for our purposes, I want to restrict our focus to this setting. Okay, so this is an adversarial error. And this here is any function you want, but it only sees one sample at a time. Okay, and a statistical query algorithm would come up with a series of queries, let's say Q queries, and it feeds them to the VStat T oracle, and then it's allowed to do whatever it wants. So let me give you an example of a statistical query algorithm. Think, for example, of the method of moments.
Quick question. Sorry, Tselil. What does it mean to see one sample in, say, the stochastic block model?
Yeah, that's a great question. So traditionally, there's been this issue where this is some reason why statistical queries are not so compatible with many of the one sample problems that we tend to think of. You know, so in the statistical query model, you know, what does it mean to get one sample of the stochastic block model? Yeah, one issue is that if you give the statistical, I mean, what you can do is you can ask a query, you know, is there a community structure in this block model if you see the whole block model at once? So you sort of have to set up your distributions in a way that it makes sense. So I personally think that the most compelling version of the stochastic block model for statistical queries is that your sample is you see one edge at a time. So this is kind of like a sort of diluted block model.
Okay, thanks.
But you can also have other, I mean, there's alternate ways to set it up as well. You can have, you know, bipartite block models and you see, you know, one side is fixed and the other side you see. Okay, anyway, so yeah, that's a great question. Okay, so in order to think of how you could use VStat algorithms, think, for example, of the method of moments, right? So here, all you want to do is you want to compute moments in your distribution, and based on that, you can do hypothesis testing. So there are many settings where method of moments is used. Statistical queries is appropriate for those settings, as long as you're willing to have some errors that you would expect to get. Oh yeah, let me just also say that VStat T is supposed to mimic the errors that you would get if you had T independent samples. So this is the kind of sort of tolerance that you would get for T independent samples under Chebyshev inequality. Okay, so the statistical query model was proposed by Kearns in order to get a noise tolerant paradigm for algorithm design. But since then it's been extended to a broader set of sort of statistical settings, not just for learning Boolean functions, which is what Kearns was thinking. And a particularly useful notion that has emerged is the notion of statistical dimension. Okay, so the statistical dimension is defined as follows. So I have my set of alternate distributions du, and I define the average correlation over this alternate set A to be the expected value over U and V chosen uniformly at random from A, or according to the distribution mu over A, if you'd like, of the correlation between the two distributions centered around one, absolute value of that. Okay, so I'm not going to say much about why this measure, you know, why does it make sense? But the statistical dimension of A for sort of T samples can be defined as follows. So it's the maximum value of Q such that for any 1 over Q fraction of the support of A, the correlation in that subset of the support is at least 1 over T. Okay, so there's a lot of kind of double negatives in that definition, but basically what it's saying is, what is the smallest fraction of distribution where I still have average correlation at least 1 over T. Sorry, I think here it should be at most 1 over T. That would clear things up. Great. And Feldman et al. In 2013 proved that if you have statistical dimension T at least Q, then you need at least Q VStat queries. So any VStat algorithm requires at least Q queries. So if you can lower bound the statistical dimension, then you can lower bound the complexity of statistical query algorithms. Okay, so what we're going to do is we're going to compare polynomials versus statistical query algorithms. But before we do that, it would be good to kind of take stock of the similarities and differences between the two settings. So in the VStat framework, our proxy for running time is the number of queries. Whereas here, the proxy for running time is something like n to the d, m to the k for degree dk polynomials and m samples. For VStat, instead of working with samples, we have a kind of a error tolerance. So if in VStat t, our error tolerance is plus or minus 1 over square root t. Whereas for degree dk polynomials and m samples, we really get to see m samples. SQ algorithms have the advantage that the queries can be computationally unbounded. Meaning you're allowed to ask queries that require brute force in order to compute. Whereas for degree dk polynomials, the degree restricts computation. On the other hand, statistical query algorithms only get to see one sample at a time. Whereas our polynomials get to see all m samples concurrently. So because of these differences and similarities, there are some problems that are always going to be easy for statistical queries, but hard for low degree polynomials. So one such example is exactly the example that Afonso brought up in the question earlier, right? So like the D null is Erdős-Rényi, and the DUs are block models, model graph in the hard regime. So if the SQ model gets to see the whole graph at a time, if one sample is the full graph, then it can just run the maximum likelihood estimator as a query, right? It can ask, you know, what is the likelihood ratio for the sample? Is it bigger than some threshold? And then it can know, whereas a low degree polynomial can't compute the likelihood ratio. Not the full likelihood ratio anyway. And for that reason, statistical queries will outperform low degree polynomials in this setting. Okay. On the other hand, the fact that low degree polynomials get access to all m samples at a time means that they sort of have an information advantage over statistical query algorithms. So there are problems that are easy for low degree polynomials, but hard for statistical queries. One example is if the null distribution is just random vectors over the sphere, and the alternate distributions are random over a low dimensional subspace. Think of the dimension as being like a constant, right? So what a low degree polynomial can do is it can take two samples, compute the inner product, and check how that compares to the inner product of two completely uniformly random vectors. But statistical query algorithms don't have access to two samples at a time, therefore they can't do that, right? And they require to be able to actually guess information about the low rank subspace. All right, so this hopefully makes it clear that we can never show that polynomials and statistical query algorithms are absolutely equivalent, but what we do show is the following. So if neither algorithm can cheat, then their performance is the same. On a more technical level, what we show is that if you have a high dimensional hypothesis testing problem, and k is any even integer, then first, if the high degree information is uninformative, then degree dk LDLR m lower bounds imply that statistical query algorithms require at least m over q to the 1 over k samples for any q. So like my favorite instantiation of q is to take q to be 2 to the k, and then this says that SDA of m over 2k is at least 2 to the k. Right, so here we have algorithms running in time n to the k roughly. And we compare that with algorithms running in time 2 to the k, requiring a similar number of samples. Now, we need a condition like this, because if we didn't have it, then statistical query algorithms could sort of cheat by asking computationally difficult questions. But notice that the kind of condition that we need isn't on the m sample. It's not on the m sample likelihood ratio. It's only on the k sample likelihood ratio, right? So this is so to say that something fairly non-trivial is going on. If statistical queries could see all m samples, they could tell the difference. But as long as k samples don't give them an advantage, then the power of these algorithms is equivalent. Okay, and we also show a converse result. So here, this condition for part 2 says, if k samples are not too informative, then the same kind of regime of statistical dimension lower bounds imply LDLR lower bound for the same number of samples. Okay, so if for any q, the statistical dimension for m over q to the 1 over k samples is at least q, then the degree infinity k LDLR is bounded. All right, any questions about the main theorem statements? I realize that they're a little dense maybe.
Yeah, I think it's okay. It takes a bit of time to parse, but yeah, there's some questions, but about other things, so I'll ask them in the end. Yeah.
Okay. All right. So when you look at this condition, these conditions, it's not really clear when these conditions are met. So, but as corollaries, we deduce kind of theorems that hold pretty broadly. So consider the following setting. So suppose that your alternate hypothesis class is robust to noise, meaning like if you take each sample and you perturb the coordinates with a little bit of IID noise, then it's still a valid hypothesis testing problem. There's still a difference between the null and alternate distributions. Then if you take the degree log m over the amount of noise k LDLR, that it still implies statistical dimension lower bounds, right? So so what this means is that like n m to the log mk time polynomials are equivalent to SDA m over 2k greater than or equal to 2 to the k. Okay, so with only a logarithmic factor loss here, which we sort of expect because of the because of like the loss when you're computing spectral algorithms, these two settings are equivalent. So the proof is quite easy based on the theorem on the previous page. What you do is you look at the high degree part of the noisy distributions. And because you're applying entry-wise noise, you know that the high degree part gets attenuated, right? So this is at most rho d 2dk, sorry, rho to the dk of the non-noise version. But because we also assumed a bound on the norm of the k-sample likelihood ratio, this is bounded by 2 to the k over m to the 2k. Because we chose D to be like log m over log 1 over rho. Okay, and this is much less than 1 over m to the k, so we met the conditions of the theorem on a previous page. Right, so basically the TLDR is that in noise robust settings, by paying an extra logarithmic factor here in the degree, you get the equivalence of low degree likelihood and statistical queries. In a number of other settings, we get even stronger quantitative dependence. So for example, if you are trying to hypothesis test product measures over the Boolean hypercube or even Gaussian measures, then the degree 1k LDLR implies the corresponding statistical query lower bounds. And this can be extended slightly, like if you want to have a mixture over very few product distributions, you can do it there too. So, and then based on these corollaries, what we're able to do is deduce new kind of free lower bounds, right? So we're able to take the SDA lower bounds for sparse PCA, or sorry, the LDLR lower bounds for sparse PCA and deduce SDA lower bounds for sparse PCA, which were not previously known. Same thing for community detection. We could do the same thing for tensor PCA, random 3-set planar clique, but for those problems already SDA lower bounds have been proved, so it's a little bit less exciting there. Furthermore, we're able to go in the opposite direction. So we're able to take a SDA lower bound for learning Gaussian graphical models and get from it an LDLR lower bound. Here, in this case, we didn't get like a very interesting result technically, and that we didn't capture information computation thresholds, but still it's very surprising to be able to prove an LDLR lower bound for this problem at all. So it's kind of more interesting on a technical level for nerds. Okay. So yeah, so in some sense we're really living the dream. We were able to take lower bounds for sparse PCA against low degree polynomials and get lower bounds for statistical queries. I was going to do a sketch of the proof, but it really looks like we don't have that much time. So what do you think? Should I skip it, Afonso?
Yeah, maybe we can go. Maybe you can skip it. We can go to questions, and then we can. Okay. If you have time, we can stay a bit later. And I'd like to see it, but
okay,
maybe we can. Yeah, just skip it, go to questions, and we can come back to it.
Sure. Yeah.
If that's okay with you.
Yeah, no, that's totally fine with me. All right, so yeah, so the recap is very similar to what we just saw before the proof. But yeah, the TLDR is we prove that if neither model can cheat, then LDLR lower bounds are equivalent to SDA lower bounds. And we specialize that to show that in noise robust settings and in product measures, the model can't cheat unless like individual samples are too informative. Okay, so one question is what kind of comes next? So I mean, I think the kind of big picture goal is to fill in this graph as much as possible. So there's some reason to hope that using this pseudo calibration framework introduced by Barak et al., one could relate convex programs. Let me make it blue so that it's clear it's speculative. One could relate convex programs to low degree polynomials. These sort of arrows might be able to be quantitatively strengthened. One could relate them back, and so really the dream is to be like Iceland Air instead of like United Airlines. But even zooming into what we proved about statistical queries versus low degree polynomials, there are some models that aren't captured in our lower bounds simply because SDA lower bounds are not good lower bounds. Do not characterize SQ. Meaning there are some settings where, because the likelihood ratios blow up to infinity too fast, like for example in the case of mixtures of Gaussians that are too non-spherical, the likelihood ratios blow up to infinity too fast, so you can't hope to prove SCA lower bounds, but it still may be possible that no statistical query algorithm succeeds. And it would be nice to have a result that sort of captures that as well, even for this equivalence. All right, great. Thanks everyone for your attention.
Thanks so much for the great talk. It's hard for everyone to clap when we hear, but analysts can. Okay. So we'll open the questions. There's quite a lot. I'll try to manage this. Okay. Okay, so I'll try to go chronologically. So someone asked right at the beginning, why is it that you can't handle mixture of Gaussians? Because you made you had a list, and then your red circle conspicuously missed one of the lines.
Okay, so that is a great question, and it goes to the definition of SCA. So the issue is that in the setting of mixtures of Gaussians, this quantity is sometimes infinite. So really it's an issue that the chi-square distance between two Gaussian distributions can be infinite. And SDA, the statistical dimension lower bounds, are